Hello again. Today we're going to be looking at the oscillation case as opposed to the exponentially decaying case. And today mainly focusing on some background with complex numbers and why changing to I omega from lambda means that we're actually looking at oscillation case. So it's giving you some of the background of why that is actually oscillation. It's quite easy sometimes just to do the algebra and turn the algebra and not really understand where this comes from. So hopefully after today's video you have a clearer idea of that. Okay, I'll hand over now to the board. Okay, so working through on the board today, we're considering this case when we do dx by dt is I, of course I is square root of minus 1 omega x, and my claim is that this gives sinusoidal solutions. But I just want to show you exactly where that comes from, because often we just use this, assume x is a complex number now, and just turn the handle on the algebra, and that's fine. But very few times these days it seems we go back to the basics and realize what we're actually solving and what we really mean. So if we call this A, really mean by A is that we take the real part of both sides. So if we take the real part of dx by dt equals the real part of I omega x. So remember now, x is complex, omega is real and positive, and omega is basically going to be your frequency of your, is essentially the frequency of your wave of, doing invert commas because it's scaled by 2 pi of wave. Okay, so what I wanted to show you that's true. So my contention then is that the true solution is x star, and if we write it down in this case, we have the real part of the true solution x star is going to be this, which is A cos omega t plus B sine omega t. So I want to just show you that what we're actually solving is cosine and sine solutions, and depending on these, so A and B are real constants, so all this thing on the right side is real, set by the initial conditions. So I'm going to call the real part of x y for a convenient sake, real part of x star y. So what we're thinking of is y, which is real part of x star, is a solution in time which has some initial conditions which set these constants little a and little b, and then off it goes, oscillating in time. So whilst it's quite quick to get to see when you use the minus lambda right hand side that we've done before, that it's exponentially decay, it's just a few more steps to realize that actually when you're solving what is it actually ETI omega t, when you do it algebraically, you're actually solving this thing. Sorry, I've got a sign wrong here. That should be minus. Okay. Actually, I should use my rubber, shouldn't I? We're digital at the moment. There you go. Okay, back to the pen. So these two solutions. So I just want to show you that if I differentiate this, I get the real part of dx star by dt, I end up with the right hand side, right? So this is just going to show you how that works. So if I do dy by dt, which is the real part of dx star by dt, so here is, i.e. what I'm looking at is the left hand side of ODE, yeah, dx by dt is something. So we want to actually show that if we do the real part of dx star by dt, or dy by dt in this case, we end up with the right hand side, and then that all fits together. So if we just differentiate what was a cos omega t minus b sine omega t, we then get minus little a omega sine omega t plus b omega cos omega t, right? And then we can do a little bit more of manipulation now. We can now factorize this back into complex numbers. That actually is a real part of a plus ib, so a complex constant if you like, times I omega times cos omega t plus I sine omega t. And you now can see maybe why I've set this up in the way I've done, because cos omega plus I sine omega t by Euler's formula is just e to the omega t. So, and there's another curly bracket that I can't get on the screen there. Let's see if we can fit it all in a bit better. Okay. So that then equals the real part. Now if I call a plus ib x naught, so if I call this complex initial conditions, this is our initial conditions, and I then have I omega, and by Euler's formula I know that this is e to the I omega t. So this is then the link between what is, I've started off with a real sine and cosine that you can plot out depending on the initial conditions, and it's linked then to the e to the I omega t solution by the real part. And this is what I'm sort of repeating a few times here, that we often quite sort of quickly with this sort of analysis, and you'll use this type of thing a lot if you do anything to do with waves, any analysis to do with waves, you'll use some e to the I something solution. But quite often we drop the real brackets bit. So I just thought, well, at the outset, whilst we're still at stage 2 in your degree, let's just remind ourselves exactly what we're solving. Okay, so if people are absolutely rigorous about this, put the real parts on there. People are a little bit sloppy about it, or just want to do it shorthand, forget about the real. So I just wanted to show you how the e to the I omega t bit links with the real solution. So we actually are solving for sines and cosines, but it's much more convenient just to put them into e I omega t. Yeah. So of course, let's just finish up. That equals the real part. So of course, e to the I omega t is just your x naught e to the I omega t is just your true solution. So it's I omega x star. Because x naught times e to the I omega t is just x star. And of course that then is just equal to the real, well, I don't need to do it actually because we started off at the top here. So this is then the right hand side of ODE. So it's kind of a very loose proof, if you like, that something with sines and cosines superimposed, of course, it fits this equation. Okay. So I could have just pulled the wool over your eyes and just jumped straight in and used e to the I omega t, but I thought it's useful to know the background of using that solution at least once in your undergraduate career. So if you do a fourth year course on waves in the atmospheres and oceans, then you'll realise it'll be the very same machinery you're using. Okay. Okay, so that's one thing. ETI omega t corresponds to sines and cosines, and so changing to I omega on the right hand side is just like changing to oscillation. There's another observation on this equation before we get into stability analysis. So another observation about dx by dt equals I omega x. Okay. If we differentiate it again, we get this one, d2x by dt squared equals I omega is a constant, and dx by dt. But of course we can then substitute again dx by dt into there. That gives us minus omega squared x. Okay, so my question is, and if I was in a real lecture now, I'd ask, just pause for a bit and say, what's that equation of? Where did that come from before in your education? Now looking back either to last year or even to your sort of A levels. Yeah, just pause for a couple seconds to have a think of it. So where's this equation? The answer is it's in simple harmonic motion. Okay, so this the equation for a pendulum, e.g. a pendulum, is governed by this, and that of course has oscillatory solutions, sine and cosine solutions. So those are two angles. You can differentiate the equation and show you've got a simple harmonic motion equation, or you can take the real part of a cosine plus a sine and show that that corresponds to the E omega t solution. Okay, so let me just talk a little bit about the initial conditions that we're setting up here now. So initial conditions. Remember, our solution is a real of x star, and this is a slight mistake on the correction on the lecture notes. I put it as x star, it should really be the real part of x star. Small correction there. Is the real part of a plus ib, which was set by initial conditions, and then cos omega t plus I sine omega t. Which equals a cos omega t minus b sine omega t. Now if we set the real part of x star at t is 0, so the initial conditions, to be 1, that means that then that sets our initial conditions. That means that a has to be 1, the solution projects totally onto the cosine solution, and b has to be 0. A equals 1 and b equals 0, which implies the real part of x star is cos omega t. Okay, so depending on the initial conditions, you project differently onto the cosine and sine solution. Okay, so that's a little bit of background to this equation now that we're looking at. Dx by dt is I omega x. Remember, x is now complex, but really when we solve this, we're thinking about the real parts of each side, but we're going to drop the real parts now. So we now need to make another sort of inferences or observations about the solution before we can analyze numerical methods of this. Okay. So remember, we're considering two cases here. We're considering exponential decay. We've done that. for Ford-Euler, for example, and also oscillation case. And although those are just two cases, they actually are quite representative of a large range of cases. You know, you will have a large amount of phenomenon and solutions of ODEs that are maybe a superposition of the two. You know, you have an oscillation which is decaying with time. So they're actually very useful paradigms. You know, so this is what we call the oscillation case. Just to repeat. So the first thing about X star, the true solution, is that complex modulus remains of X star is constant. So if X star is X0 e to the I omega t, so here remember X star is complex, X0 is complex, then the X star now is a complex modulus. It's a complex modulus of X0, which is a complex modulus of e omega t. And of course the complex modulus of e omega t is simply 1, so it's simply X0. And if X0, remember, is A plus IB, our initial conditions. So X0, and this is a first thing to remember. Let's go to, so we're going to do complex modulus of X0 where X is defined, so we're going to find complex modulus of X0 where X0 is A plus IB. Remember, is those bars, vertical bars, is a complex modulus. Okay, not absolute value, or it's because it's not real. So the important thing is we don't just square the I bit. This is unfortunately something that people either didn't learn properly at A level and miss out. Some people will square the A and then square the I and get A squared minus B squared. No, that's not the way to do it. You do X0 square modulus squared is A squared plus B squared. Okay, remember when we have complex numbers, we're now on an Argand diagram where we have real part and we have the imaginary part, and of course then A lies along that axis and B lies on that axis, and then X0 is the hypotenuse, so you're using Pythagoras. So this should all be revision of your complex numbers, but I'm conscious that people either, you know, it's one thing to learn it in one context and sometimes it's harder to apply it in another context. But please remember this, when you do a complex modulus, you do the squared, you do the sum of the squares of A and B, and you don't just square I, okay? The reason being is it's because it's you know, a Pythagoras thing. Okay, so and I'll give you another example in the notes. So just going to check on the time. Yes, so I think that's a good place to pause. I've sort of given background to today. I've given quite a lot of background to this oscillatory solution, and next time I'm going to then go into the stability analysis of the oscillation and how we use complex numbers to do the stability analysis of the problem. Okay, so see you next time.